Here we sharpen up correlation by putting an actual number on it. We'll meet two measures: Pearson's coefficient for straight-line trends and Spearman's for rankings, and learn when to reach for each. A scatter graph is great for a first impression, but looks quite strong, won't cut it in a real report. A correlation coefficient boils the strength and direction down into a single number, and every one of them lives between -1 and +1. We'll study two: Pearson's product moment coefficient and Spearman's rank coefficient. Which you pick depends on the kind of data you have and the shape of the relationship. Let's get a feel for the scale of the correlation coefficient R. An R of +1 is perfect positive linear correlation, every point sitting on a single rising line. An R of -1 is perfect negative correlation, all points on a falling line. An R of 0 means no linear correlation at all, so the sign tells you the direction, and the size, how close to 1, tells you the strength. In real life, you never get a tidy +1, so how do you read the in-between values? The correlation coefficient R near plus or -1 means the points cluster tightly around a straight line. Near 0 means barely any linear pattern. As a rough guide, an absolute value above 0.8 is often called strong, around 0.5 moderate, and below 0.3 weak. But treat those as guides, not gospel. Always glance at the scatter too. And remember, a strong R still doesn't prove one thing causes the other. Pearson's R measures the strength of a straight-line relationship between two quantitative variables. The formula is the correlation coefficient R equals SXY over the square root of SXX times SYY. Here SXX is the sum of x squared minus the quantity sum of x squared over n. SYY is the same idea for y, and SXY is the sum of xy minus the sum of x times the sum of y over n. Because it uses the actual measured values, Pearson suits interval or ratio data that follows a roughly straight line. The method has 4 steps. First, tabulate with columns for x, y, x squared, and xy, and total each. Then apply the 3 sum of squares formulae to get SXX, SYY, and SXY. Combine them. The correlation coefficient ER equals SXY over the square root of SXX times SYY. And finally, interpret, stating the direction from the sign and the strength from the size, and adding your causation caution. Let's tabulate 6 paired observations of x and y. We add columns for x squared, y squared, and xy, and total every one. That gives a sum of x of 21, a sum of y of 40, a sum of x squared of 91, a sum of y squared of 316, and a sum of xy of 168. Careful, tidy tabulation is what stops silly arithmetic slips. And those 5 totals are everything Pearson needs. Now let's crunch it. With n equals 6, SXX is 91 minus 21 squared over 6. That's 91 minus 73.5, giving 17.5. SYY is 316 minus 40 squared over 6, so 316 minus 266.67, giving 49.33. SXY is 168 minus 21 times 40 over 6, which is 168 minus 140, so 28. Then the correlation coefficient R is 28 over the square root of 17.5 times 49.33. That's 28 over the square root of 863.3, so 28 over 29.38, which comes to 0.95, a strong positive correlation. Let's unpack that R of 0.95. The positive sign tells us y rises as x rises. The size, so close to 1, tells us the points lie very nearly on a straight line. Put together, that's a strong positive linear relationship, and it justifies fitting a regression line to make predictions. But you knew this was coming. An R of 0.95 still doesn't prove x causes y. Always report both direction and strength. Then add the causation caution. Pearson works well under a few conditions. Both variables need to be quantitative, measured on a numerical scale. The scatter should look linear, a genuine straight-line trend. And there shouldn't be extreme outliers, which can distort R badly, since a single stray point can wreck it. If instead your data is ranked, or the relationship is ordered but curved, or there are strong outliers, that's your cue to switch to Spearman. Spearman's coefficient, written RS, measures how well two rankings agree. The clever part is that it works on the order of the data, not the raw values, so it's ideal for ordinal data like judges' rankings, league positions, or star ratings. It also copes when the relationship is monotonic, steadily rising or falling, but not actually a straight line. And because it uses ranks, it's far more resistant to outliers than Pearson. The formula is RS equals 1 minus 6 times the sum of D squared, all over N times the quantity N squared minus 1. Here D is the difference between the two ranks for each item, and N is the number of pairs. Like every correlation coefficient, RS stays between -1 and +1. An RS of +1 means the two rankings agree perfectly, and -1 means they're exactly reversed. 4 steps again. Rank each variable separately, deciding whether 1 is the highest or the lowest, but staying consistent. For each item, work out D, the rank of X minus the rank of Y. Square each D and total them to get the sum of D squared. Then apply the formula. RS equals 1 minus 6 times the sum of D squared, over N times N squared minus 1. Let's picture two judges scoring 7 entries, A through G, in a competition. Each judge's scores get turned into ranks, with 1 as the highest. Then D is the difference in their ranks for each entry, and squaring it drops the sign. In our case, only entries A and B differ, each by a single rank, so the sum of D squared is just 2. That already tells us the two judges are very nearly in agreement. Now the arithmetic, with N equals 7 and the sum of D E squared equals 2. First N times N squared minus 1, that's 7 times 49 minus 1, so 7 times 48, giving 336. Then 6 times the sum of D squared is 6 times 2, which is 12. So RS is 1 minus 12 over 336, that's 1 minus 0.036, giving 0.96. An RS of 0.96 means the judges ranked the entries in almost exactly the same order. A quick word on ties. If two values are equal, they share the average of the ranks they'd otherwise take. So two entries tied for third and fourth each get a rank of 3.5. Reading the result, an RS near +1 is strong agreement, near -1 strong disagreement, and near 0 little link. Our 0.96 means the judges almost completely agree, though, as always, agreement in ranking doesn't prove one judge swayed the other. So when do you use which? Reach for Pearson when both variables are numerical measurements, the scatter shows a straight-line trend, and there are no severe outliers. Revision hours against marks is a good fit. Reach for Spearman when the data is ranked or ordinal, like positions or ratings, when the relationship is monotonic but not straight, or when outliers would throw Pearson off. Two judges' rankings being the obvious case. Let's boil the choice down to a few questions. On data type, Pearson wants interval or ratio data. Spearman handles ordinal or ranked. On the relationship, Pearson needs it linear. Spearman just needs it monotonic, any steady rise or fall. On outliers, Pearson is sensitive, Spearman much less so. And underneath, Pearson works on the actual values, while Spearman works purely on the ranks. Whichever coefficient you use, and I'll keep banging this drum, a strong result still only shows association. A confounding variable, or plain coincidence, can throw up a high coefficient with no real link at all. Only a controlled experiment can establish genuine cause and effect. So report the coefficient, describe its strength and direction, and add the causation caution. A number never upgrades association into proof of cause. Let's ground it in business. Picture a coffee chain like Costa Recording. For each store, a customer satisfaction score and the repeat purchase rate. Both are numerical, so Pearson's R is the tool, and say it comes out around 0.8, a strong positive value suggesting happier customers do tend to come back more. Now, if instead the stores were only ranked 1st to 10th on service, Spearman would be the right choice. The chain uses that result to back investment in service training, but it still can't claim satisfaction. Alone drives loyalty, price, and location matter too. Let's draw the outcome together. A correlation coefficient turns strength and direction into one number between -1 and +1. Pearson's R, which is SXY over the square root of SXX times SYY, suits linear quantitative data, and our worked value was 0.95. Spearman's RS, which is 1 minus 6 times the sum of d squared over n times n squared minus 1, suits ranked or ordinal data, and ours was 0.96. Choose Pearson for linear measured data and Spearman for ranks, curved but ordered trends, or outlier-prone data. And a strong coefficient shows association only, never proof of cause. So that's correlation measured properly, with Pearson's coefficient for linear data and Spearman's for rankings, plus the judgment to pick between them. If you'd like more practice, Crawshaw and Chambers works through both coefficients in detail, and Corbett Maths has step-by-step videos for each that are easy to follow along with. The Royal Statistical Society's Significance magazine regularly shows correlation at work in polls and studies, a good reality check on what these numbers really mean. Have a look at the Moodle ebooks and journals for this unit. And do ask your tutor if any of the formulae feel shaky before you attempt the assignment.